Welcome back to Fat Mama Physics. In these videos, we are going to talk about kinetic energy and how it relates to the work-energy theorem. Before we do that, we want to talk about the types of energy just to give you a sense of where kinetic energy fits in the whole grand scheme of things. Kinetic energy actually belongs into a category called mechanical energy. So what that is includes things like moving cars, which is where kinetic energy fits. Later on in this unit, we will also talk about potential energy, such as gravitational potential energy and elastic potential energy. There are other forms of energy which we might see in the rest of the year and the rest of the IB curriculum, including thermal energy, EM energy, electrical energy, and nuclear energy. But today we will focus on kinetic energy, or the energy associated with something that is moving, associated with motion. So what is kinetic energy? Kinetic energy can be calculated by the following equation: 1/2 mv squared, where m is the mass of something in kilograms, of your object in kilograms, and v is the speed that the object is traveling in meters per second. Notice that it is in not velocity. Well, you could put in velocity, but because kinetic energy is a scalar, just like energy and other forms of energy and work, direction does not matter. If I have a lot of kinetic energy traveling in one direction, I can have them traveling in the opposite direction or any other direction involved. So that kinetic energy just tells you how much motion energy that my object has. So that's kinetic energy in brief. In this video, we are going to do an example, and it's going to bridge into what I want to talk about next, which is the work-energy theorem. So let's start off with this example here. We have a 830-gram snowball rolling down the slope. Here we got a mass. Assume the mass doesn't change, so assume the snowball doesn't pick up mass, it's extra snow. As it's rolling down, it starts off with 1.1 meters per second, so that sounds like it's going at that speed. After a while, the snowball increases its speed to 3.5 meters per second. So it seems like this is some sort of initial speed, and this one is some sort of final speed, which we will just put it in like that, okay? Calculate the snowball's initial kinetic energy. Well, let's do that right now. According to the equation for kinetic energy, we need the mass in kilograms, but the mass we are given is in grams, meaning to convert it to kilograms, we need to divide this by 1,000, since there's 1,000 grams per kilogram, and that gives us 3 decimal places over, 0.830 kilograms. And this is the initial kinetic energy, so this is before it increases speed to 3.5. That's the 1.1 meters per second. That's the speed we will use. And then putting everything in, and kinetic energy, I just use EKI for initial, and I put the U to show its initial velocity. So there we have it substituted in, putting in our calculator. We get 0.50215. And that rounds up to 2 sig fig 0.5 joules. This is actually a good time for you to try B, because all it's asking for is the snowball's final kinetic energy. So it's a good time for you to pause the video right now and work it out. Since it won't take very long, I'm just going to do it right here. So EKF for final, 1/2 mv for final, speed, I guess, squared. We have the v final, and that is 3.5 meters per second. Putting everything in, we get pretty much the same thing as before, but substitute it, and in our calculator, we get 5.08375. Rounding to 2 sig figs, we get 5.1. Not bad, eh? And see the snowball's change in kinetic energy. So whenever you see the word change, you might think of the sign delta, and then what change means is that property's final state minus its initial state. And in terms of kinetic energy, That's just final kinetic energy minus initial kinetic energy. The final kinetic energy we calculated in B, without rounding out the values, 5.08375 joules minus the initial non-rounded value, 0.50215 joules. Putting in our calculator, we get 4.5816. Rounding to two sig figs, we get 4.6 joules for change in kinetic energy. You might be wondering, why did I ask for change in kinetic energy? She's up to something. There is a reason, and that is question D. Question D is asking for the work done by the net force acting on the snowball during its acceleration from 1.1 to 3.5 meters per second. Assume the snowball experiences no rolling friction or other resistive forces. Just a quickie here. This rolling friction, you might or may not have seen this word before, but since the snowball would be rolling down the cliff and not sliding down, the slope, there is a different kind of friction that we use instead, and that's called rolling friction. Sliding friction wouldn't be appropriate here because if in order for the snowball to roll, it cannot slide or slip along the incline. It's kind of when you are driving on an icy path and you don't want to skid. That's the same idea. You want your tires to be rolling and not your tires to be sliding across the icy path. And the rolling friction is associated with rolling, not sliding. So that's very important. In this case, we don't care about that because there is none of those friction forces or other resistive forces, but just in case you were wondering. Now we need to find the work done by the net force acting on the snowball. So this is something new. Before, we used to find the work done by a specific force acting on an object. In this case, it's not just the one force. But let's do draw a free body diagram first. We have the gravity acting on this snowball. And since this snowball is on an incline, the normal force is perpendicular to that surface. So it looks like that. There is no friction force or no rolling friction, so that's it. There's no other forces acting on the snowball that hinders its motion down. Don't forget, if we're dealing with an incline, your axes are tilted, in which the x-axis is along the direction of acceleration of your snowball, which is down the incline for convenience, and the y perpendicular as such. And it's very convenient that it's parallel with the normal force, meaning we need to split Fg into its components. If you don't remember how to do that, refer to a previous video on inclines. So here we have Fgx, and downwards we have Fgy. Based on geometry analyses, this angle here is 28 degrees. If you don't remember how to do that, again, refer back to a previous video. Since the snowball will only be going down the incline, it will not be accelerating up or down or anything, so the net force would be going down the incline, which is only our Fgx. Notice Fgy and Fn will balance, and the fact that the snowball will not be accelerating along our y-axis. So our net force will be just Fgx. What is Fgx? Well, we know the hypotenuse is Fg, and relative to this angle over here, the 28 degrees, Fgx is opposite to that, which means that is equal to Fg sine 28. We also know Fg is mg, so we can just write that instead. Mg sine 28. What is the question asking for? Let's double check. The work done by the net force. So that is W is equal to F net times displacement. Well, we know that this snowball is going to go down this incline, so the F net and the displacement are parallel to one another because they point in the same direction. We don't need to worry about a cosine theta anymore. The angle would just be 0 between F net and S, displacement, so cosine 0 is just 1. We don't need to care about it. If we want the work done, we need the F net. F net is just mg sine 28. We have gravity, mass is given in the previous part of the question, which is 0.830 kilograms. So if we have F net, we just need the displacement, okay? Let's calculate Fnet first, so we have that value. Mass times gravity, 9.81 meters per second squared, and sine 28. Okay, that gives us 3.822 in newtons, which will need all its digits. So we have Fnet. So we need S, or displacement. To find the displacement going down the incline, we have the final velocity, which is 3.5 meters per second squared. We have the initial velocity, which is 1.1 meters per second squared. And we want the displacement. And to get displacement, we either need time or the acceleration, because we can then use one of our kinematics equations to solve that. I can quickly write them down here for your convenience. It's going to be quite difficult to obtain the time because we will need acceleration, which we don't. But we can get acceleration. Why? Because we have Fnet. And we know Fnet is just mass times acceleration. So if we have Fnet, we have mass, we can then find acceleration. If we have acceleration, we can use one of these kinematics equations to get the displacement. Which one would that be? If we take a look, it looks like it's going to be this one over here, where it has acceleration and we need the displacement. So let's just set this equation up so we can use that later. So I have subtracted initial velocity squared on both sides. I'm going to isolate for displacement here by dividing both sides by 2a. I get v squared minus u squared divided by 2a. So to find displacement, we need the acceleration, which then we will need Fnet equals ma first. To solve for a, let's divide both sides by mass. Hey, we have Fnet up here. We already know Fnet. And mass is just 0.83, which I wrote up here. So let's do that. Making sure we don't lose any digits. Okay, so putting in our calculator, we get 4.6 ... meters per second squared. Remember, we got to save all the digits. And now we can use this value down over here. Final velocity is 3.5 meters per second. Initial velocity is 1.1, and acceleration is 4.6 meters per second squared, as what we just calculated. That gives us 1.1985 ... meters, in which we will save all the significant digits. Okay, now we have the displacement as well. We can go ahead to calculate work, in which 3.822 is our Fnet, and displacement is 1.1985. We get 4.5816, which we were going to round to 2 sig figs 4.6 joules. Wait a minute. Where else did we see that value again? Let's go back. Oh my gosh. Isn't that just the Snowball's change in kinetic energy? These are the same. Why? And how? And pretty much, that just means that I did all this work here for nothing. I could have just found the change in kinetic energy, and that gave me the work done by the net force acting on the snowball? What? A shortcut? Ooh, we love shortcuts. We need to try and play around with some of these equations. Maybe that can give us a hint at why the change in kinetic energy is exactly the same thing as the work done by the net force on the snowball. I also have a challenge for you that you can try. It is this one. Try the same question here, but instead with a coefficient of kinetic friction of 0.20. In fact, try any coefficient of friction. See what you find. Will you find the same thing? Ooh, interesting, eh? Anyhow, stay tuned for the next video, which we will answer this question. Why is that the work done by the net force is exactly the same thing as the change in kinetic energy? Alright? See you next time on Fat Mama Physics. We are signing out.